Let's get started. So my name is Peter. I'm a network engineer at Facebook. And today I'm talking about network troubleshooting. So as a disclaimer, I was listening to talks before. I will not be talking about Python, BGP, optics, machine learning, JavaScript, or anything fancy. Just a good old school network debugging and troubleshooting. Because really, there are two things I like about networking. First one was routing, and second one is troubleshooting. And I'm pretty much done with routing these days. So the only thing left is troubleshooting. So I want to start the conversation by by thinking about how applications see the network. The thing is, when we debug things, we often focus on the low-level artifacts. But the reality is that we really should be thinking more about applications and how they interact with the network. So application world is actually pretty difficult. People who write networking code have to deal with lots of, I call it course of layer of abstractions. You have layers of interaction, which probably all heard about in school, these application, session, transport layers. But it's hard to realize how much they affect networking until you start debugging. So if you look at what applications use at the high level, at layer 7, it's RPC, like thrift or gRPC, or message passing if it's MPI, or a streaming, these high-level concepts which don't naturally map to low-level primitives. At the same time, we have a pretty old-school API, sockets API, that's pervasive everywhere, which was written like in the 80s and was probably not really considering the realities of modern world, and say deals with TCP, which is just a byte stream protocol. And in reality, when you write your networking code, you end up dealing with lots of these TCP wires that are very peculiar and hard to deal with. So this is an example of a kind of lame diagram, but it gives you an idea of how a simple RPC client can talk to multiple RPC servers. So in a classical setup, be it microservices or whatnot, you have a client application which talks to a group of servers, right? So you have a connection pool, typically TCP connections established over network, and you send multiple requests over these pseudo wires, TCP connections. And the problem is you don't really know which one you would choose, right? Your request will go over some of the TCP connections, hit one of the servers, and come back. And in between, you have load balancers, you have switches, you have buffering, and so on. So all that, in general, makes it pretty hard to map application traffic into the network. And like from perspective of TCP, network is a very simple concept. So TCP follows the famous, maybe infamous, end-to-end principle, right? You just treat the network as a black box. You have this end-to-end feedback loop to control the congestion, and you treat the network as a pipe of bytes. You just push bytes, and you imagine they actually make it through. And if you want to actually understand how tricky it is, try to follow through RFCs and figure out how a push bit is being set and used by TCP. I always think this is a good example of trying to understand how complex this interaction between the sender, network, and transport could be. So what's important from TCP perspective, it models the whole network, this vast number of devices, as a single bottleneck link, and tries to estimate its throughput, right? And throughput is what defines your performance in TCP. So there's another crappy diagram, but it shows you, hey, from all these devices, send and receive buffers, we only really try to detect this one bottleneck in the network. So this is how much TCP compresses the knowledge of a network, right, into one very simple model. And actually, there are very good reasons for that, which we can't discuss here, just too many details. For this simplification, this is what made internet actually work. but at the same time, it costs a lot in the visibility of network performance. And if you're curious, you want to compare this to the networks they built for HPC, for high performance compute, specialized interconnects, MirrorNet or InfiniBand, and see how we combine hop by hop flow control, buffering, adaptive routing together to achieve a very smart fabric. The TCP assumes pretty best effort and dump network, and that complicates a lot of debugging and network understanding. Because in reality, behind this black box, you have lots of nodes with buffers, right? In a typical data center, in a big data center, you have maybe few thousand devices easily. And every time you send packet between two endpoints, you cross 10 buffering endpoints, and your packet may be dropped or buffered anywhere. And worst even, in data centers, because we all like these big fat trees, we end up having lots of paths, right? And it's really hard to predict which one you're going to take. And often your application ends up using all of them. And worse even, in the backbone, we have traffic engineering. We have this out-of-bandwidth TE logic, which keeps flipping back and forth and changing the paths, which makes debugging pretty much impossible, because the moment you kind of fixate the path, it already has changed, right? And this was my experience actually debugging something in the early days when I just joined Facebook. You just run traceroute and hey, I got something, and 5 seconds later it's gone, and it can't be stable. So that dynamics and the vast diversity of networking paths is another dimension of a problem, right? What makes it difficult to troubleshoot these things. This section is about how can we tell if network is okay, because it's very common in every investigation to blame the network, right? It's almost, I think, it's infamous saying. So typically the flow goes like this. Some application metric, hopefully we have them, right? SLO detects with regression in some performance, like QPS drops, right? Or throughput decreases, or you miss a deadline for copying a file or something. So then, of course, people start blaming network or something else, but often network always in parallel. Like in every incident I was involved, we often fork these investigations network in parallel with something else at the same time. But network is always a culprit because network is in between of everything. So people are just used to thinking it's a problem, right? So very common first step people always do is look at the dashboards or counters and try to find packet drops. Because, well, realistically speaking, most of the problems, almost all of them, come from packet drops. For some reason, be it congestion or a gray failure or something else. If you can't find packet drops, people try to find what correlates to this event. Say, my regression started at 1 o'clock, what else happened at this time? So these two methods, I think, are most prevalent in every troubleshooting. Because it's kind of heuristics, you try to find something obvious which correlates, or the strongest indicator of a problem, packet drops. If these two things don't work, we move to black magic phase, right? And black magic means, okay, you have to find somebody who's been networking for a long time, who knows how to really use TCP dump. But before that, I think actually a very common pattern is just to hope things go away. And I'll be honest with you, the strategy of just ignoring a problem works really well in most cases. I've seen this working very well many times, because there are so many problems that happens quickly and disappear, you can't really trace them all. But anyways, then you find some person who knows TCP dump and ask them, hey, what's going on? They usually follow the same pattern. They do trace route. They try to find the paths that hopefully application traffic should follow, which is actually very non-trivial, because remember this picture, when they have multiple paths for a RPC call, you have to trace them all, right? And that's not non-trivial, very non-trivial. And if you are lucky, you can reproduce a problem using, say, iPerf or NetPerf or whatever your favorite one is. And then you nail it to a particular link or device in the network, which I can tell you could be very tricky, because you may have, as I said, how many, we have like probably 200 boxes in one layer in the network in data center at Facebook, right? So any one of them could be a problem, right? And of these each of these boxes, we have like how many, like 48 links, for example. So it ends up like having like 3,000 links at one layer, which may be problematic, right? Um, so this is still a black art, right? Every investigation I've seen so far almost always involves humans, right? It can be automated. You know, like 7 years ago, I believe I had this hope like, hey, we can automate these things because seems easy to find packet drops and attribute them to regressions, but we're still not there. I mean, it sounds a bit green, but it also tells you how much potential for improvements here ever is here. So now to the kind of core idea of this talk, this one weird bit trick or whatnot, moving from this black box of networking to more of a white box, gaining more visibility in the network. So there are two dimensions, but before I get there, let me tell you that inspiration for this idea came from a very well-known methodology of recording the TCP transmissions on the host. So typically network engineers don't deal much with the host side, but these days they more and more start doing that more and more frequently. So on the sender side, you can instrument kernel, be it Windows or Linux, to report the TCP transmission events. So kernel can give you a hook using like BPF program touch point, and you can record when you have a transmission and capture the call stack, application name, and other attributes. And then you can have the stats which you export to some data source, like what people have these days. I mean, Grafana or something. Unfortunately, or fortunately, we have different systems at Facebook, always custom, but you dump this data to some data source. And then you can see, oh, okay, this machine has more transmissions than the other. And you can try to group them somewhere else. But the problem is that all this data about the transmissions is hard to map to the network. You can group it by host, by the host layer or structures, but you can't tell exactly where the network this happens. You can roughly infer that for traffic going from X to Y, there's more transmissions on the WAN network, but you can't tell exactly where this happens. So that's, you know, like the mockery of it. You know there's a problem, but you can't pinpoint it to the network. Okay, so the first idea, which I think has been in the works for a long time, is to record or expose network paths in the packets. So typically, the way this is done for like maybe 40 years, you look at the TCP connection, if you know which one you're looking for, and you do TCP trace route using the same source and dest port pairs. So you try to trace exactly the path the connection takes in the network. It's actually pretty powerful if you get it right, but you need to know which connection to trace. But then you can look at every hop on the path and infer what happens where. And TCP trace route is a well-known tool that people often use. Unfortunately, it's manual. It requires some, you know, intelligence and habits to use it efficiently. But then, I think probably 5-6 years ago, Barefoot and VMware came with this idea of in-band telemetry, or INT. It was pretty powerful, actually. Very creative. You know, they were trying to sell this silicon Barefoot, saying, "Hey, we can take your packets and embed some data in them as they fly through a switch." And the most useful one seems to be like switch name and port name, for example, right? Because it tells you exactly which paths you have crossed in the network, right? And then on the receiver side, you can look at this payload additional fields and say, oh, hey, this connection, which is experiencing some problem, crossed these devices. And the overhead is low if your networking can do that. And the idea is essentially pretty powerful. So I think there was many proposals. A bunch of them are now in IETF. I believe it's been in IETF for 5 years. Comes out, it's really hard to standardize this in-band data embedding because none of the protocols we had were designed to take this data on. Like one of the ideas I was involved in personally was trying to use TCP options to encode hop IDs. But then TCP options is such a precious and scarce resource, you can't really fit much data there. So there's a whole, I think, epic battle in IETF about using IPv6 extension headers. But well, if you go to IETF, you probably know about that. But we've always run into this issue. IPv6 is great, but most people don't have it still. And then extension headers are hard to process in hardware, and so on and so on. So that's a whole other debate about IPv6 and ossification of hardware. So we won't get there. But I think the main problem with the in-band telemetry is that it's not standard, it's hard to standardize, and it also kind of, by design, it has a problem. It's abstraction leaking. You try to inject data from lower level into a higher level. Like, give one example, one problem we ran into talking to some vendor was, should we record layer 2 hops or layer 3 hops only in packets, right, as they cross it? How do we decide that? So that layer of deciding the right abstraction boundary was pretty tricky, you know. But if you're curious, there's work going on. There's actually support in some silicon, in pretty popular vendors who can do this right now. But with one caveat: you have to have all devices in your network support that, and in silicon, and then all the OSs running on devices expose those knobs to configuration, right? So for Facebook, it was a bit easier because we run our own OS, but even that is, you know, enabling feature at large scale. It's a whole other story. You know, trying to push like a small change to a large fleet, it's an epic drama on its own. So in-band telemetry, cool idea, hard to realize. I think I just recently looked at the old IETF draft I published 5 years ago, hoping it's gonna, you know, accelerate some things, and realized we made some progress, but not nearly as much as I hoped we would. Okay, now our idea, which is much easier to implement, it's about trying to tell the network, no, it's about trying to see the applications in the network. So the previous idea was telling the network path to devices. The other one, this one, is about how can I tell who is congesting this link right now, right? So it was pretty simple, actually. When you have the speed transmission on the sender, unfortunately, TCP doesn't mark this packet. It just sends you as another normal packet in the network. You can't tell it unless you receive it and see, oh, it's actually out of order, tra-la-la, all that stuff. But if you can mark this packet and then observe it in the network using S-flow sampling, you can now immediately tell, okay, on this link, on this device, I see packets which experience congestion. And these packets tend to cluster around the point of congestion, right? And then if you sample, you can actually see these applications are causing most of buffer pressure on this device. So the idea was conceptually very simple, right? The first problem was which bits can we borrow, right? Comes out with not many in packet header left, right? In IPv4, with fragment offset, but you don't really want to mess with that one. But there was one field, TTL or hop limit, was common for v6 and v4. And in IPv6, it's even better because if you change the hop limit, you don't have to change the checksum. So it's freaking amazing, actually. There's also urge pointer and TCP. It's actually a funny field because when you ask people, do you know what urge pointer is? People say, oh, there's something in the RFC, but nobody really remembers what this actually means, because nobody actually uses the urge pointer. The only use case for that was, I think, in Telnet for out-of-band data. And there's an RFC, actually, I think written by Anton Yurchenko from Cisco, saying don't use urge pointer because the interpretation of RFC was broken in BSD, and everybody copied it incorrectly. So this was a whole other story, which is very funny to pursue. But the long story short, we can use the 16 bits in TCP header for our own needs. It's non-standard, absolutely non-standard, but we have 16 bits to signal application state or anything else to the network, right? Because you can observe these packets in the network. But you know, we began small. Also, before I talk about implementation, that idea of exposing congestion in the network is not new, of course. Absolutely, somebody, you know, like every idea you can encounter was already thought by somebody before you, by some person from, I think, 90s or something. So this is called CONEX. Condition exposure is a working group in ITF, which I found afterwards and say, oh, hey, these guys already had the same idea. But they, in ITF, they did it right. They started using extension headers. So we did it correctly architecturally. But practically, it was really hard to implement because IPv6 extension headers break your hardware. So we don't break it, we just break some functions in hardware, right? Like hashing, for example, and other things. But if you're curious, look up the CONEX, condition exposure work in ITF. It's pretty interesting. It's more general than the use case I propose, but still very interesting. So we call our system TTLD. Was some acronym decryption for that? I forgot. I just based on TTL field, TTL daemon. It's poor man's CONEX. On the sender side, at every machine at Facebook, we have a set of BPF programs. It's a kernel extension programs in Linux that attach to kernel when you send a transmission packet, and mark packet headers, which constitute this transmission block as it transmits. And we tweak this upper bit in TTL field, set it to 1. So now we can say, oh, what the hell? I mean, TTL field is 8 bits, right? So what happens to machines that send packets with like 255 time to leave? Because it's very funny. If you look around and say, okay, what's the default time to leave in packets? You'll get different values for different OS. I think for Linux, it was 128. For Mac OS was 64. I actually don't remember exactly, but it was some weird stuff. So we had to deploy the TTL normalizer first and make sure that every machine at Facebook doesn't set TTL above 128 by default. So we saved this 1 bit for our own needs. And this actually was a lot of work with a team doing that, and kudos to them, because trying to push any change at this scale is super painful and tedious work. So I'm never jealous of those folks who have to do that, but I'm very proud of them, because I did this when the fleet was smaller and it was simpler, but as the company has grown, so did the infrastructure. And I'm like, man, it's pushing something at this scale, that's a lot of freaking work. But anyways, thanks to these guys, we have this working, this marking works. And in the network, we enabled S-Flow, because luckily these days, every silicon supports S-Flow. The only problem is that it's really freaking hard to collect. When they have like tens of thousands of devices, I think even more than that, it's a lot of samples to process, I can tell you. So we eventually ended up enabling S-Flow only on some layers where we suspect issues to happen more, like in the backbone. So our first deployment was only to do S-Flow on the backbone. Luckily, we also have S-Flow there already for another use case for traffic engineering, so we can collect traffic matrix. We should probably do a talk on S-Flow once, because it's such a interesting technology, but I think it was sort of underrated maybe for many reasons. But that's an amazing diagram explaining architecture of TTLD. On the sender, we hook and mark packets. In the network, we use S-Flow samplers, or actually echo counters. You can actually match in echoes on TTL field. I think most silicon vendors support that. If you want to just count precisely the number of transmits. Unfortunately, echoes do not tell you the source and destination IP addresses, right? S-Flow gives you full header, so you can tell which application sent this transmit packet. And then you can actually attribute this congestion to application sender or receiver, which is pretty powerful. So end result, network can now see congestion events. And so what is the kind of output you can get from this system? From 1 bit in a header and S-Flow. So first of all, and pretty powerful, is a heat map. You can build network graph and color the links which have more TTL bits. So typically, this corresponds to the links which have more congestion. So you can say, hey, what's a big deal? We already see congestion. Oh, well, good part is that this also detects the silent drops, something that you don't see in your counters, right? SNMP doesn't report your drop, but you still see it, right? So TTLD helped us found few issues of silent drops, right? It wasn't that frequent. This whole story about gray failures and silent drops was pretty popular 7 years ago. I think back then, few vendors, I won't name them, silicon vendors, were shipping ASICs which had lots of issues in the SRAM and parity errors because of alpha radiation and crap. So we used to always end up some random corruption errors. But I think over 5 years, 6 years, things has improved dramatically. So we see this kind of problems less frequently, at least in our silicon, our network. But that heat map is pretty powerful for humans to look at network and visualize the failures. Second one is probably most useful. You can look at the link which is hot and tell which application is contributing to this congestion, right? That's pretty powerful because in our environment, we have IP per container. So you can tell immediately, oh, this service is causing this congestion on this link. And then you can go and yell to people or do whatever something else you want. But that was kind of solving this problem of localizing the transmissions and application signals to the network. And last but not least was very interesting. I mentioned that the transmissions is a metric you can see on the sender. Now, TTL bit set, you can also count this on the receiver. So you can account the transmissions to the victim, like the receiver of the transmissions. Because otherwise, it's really hard to, on the receiver, to tell the transmissions, because what happens if you lose one packet, you get a bunch of them out of order. So you can only count packets which are out of order, but not the exact number of transmissions. So this gave us very useful metric, number of the transmits that you receive on a host, which came to be pretty useful to detect in-class problems in the network. Because it tells you, okay, this host is kind of the absorber of this congestion. Well, I wish I can say, hey, this is the ultimate system for network troubleshooting. It's only, I would say, part of a bigger solution, right? I don't think we still have a full solution. We have a few tools which are very useful. I think a long time ago, I spoke publicly about active probing at NORAD. So active probing is still there. It's very actively used system, sorry for wordplay. But this kind of passive observation tools is what we built over the last few years. And we found them very useful to augment the process of network troubleshooting. There is a list of open questions off the top of my head that can give you, say, hey, you know, like we don't have easy answers to them. Like fault localization is still an art. If you have like 10,000 links, it's really hard to tell which one is causing problem when you see an issue, right? It's impossible to tell how much congestion is bad. So the reality is congestion is a part of life in TCP. If you have many flows on one link, they do cause congestion. The question is like, how much is bad, right? And it's a very difficult question because you can't really tell. It could be like 2 flows on one link already bad, maybe, or 10,000 flows might actually still be fine, right? And it also varies a lot based on our parameters, like RTT or MTU. Actually, MTU size is never a very interesting problem. I wish I could talk about once. Like there's a whole debate about jumbo MTUs and their value. I wish we could talk about that once, but anyways. And if you're following kind of ITF and Google's work closely with this war of TCP congestion control algorithms, like VBR is a proposal from Google that is using very different logic for probing the network. And so a question comes, what's the best transport to work on this black box-ish network, like best effort networks? And still there's no answer because there's always trade-off. You can't really deploy one transport, they have a full win-win situation. So with that, I want to close my talk, my presentation. I hope this was interesting, useful. There's actually much more questions than answers, but I hope this gives you an idea and inspiration that network troubleshooting is far from being done. There's some things you can do, and I hope you find it interesting. Thank you.